authors, which was called A New Graph-Based Approach for Document Similarity Using Concepts of Non-Rigid Shapes, the utilization of graphs as a structure to represent said documents. Some previous concepts that I will talk about are the key point, the K-ring, the keywords, and the neighborhood. Well, in 3D models, a key point is a point which is distinctive in its locality and it's present at all different instances of the object. And in documents, the adapt concept will be the keywords, which are defined as the words which bring most information about a set of words inside a neighborhood, such that its frequency and the grading which is related with its neighbors are high. Here we have an example of the previous concepts. For example, we have the graph of a document because, as I mentioned before, we will be using graphs as the representation for the documents here. And also we have on the right a key point V, which will be the one in black, and the K rings for this key point stated in different colors, green, blue, and yellow. And the adapted concepts for documents will be the keyword, which will be N, as you can see on the right, and the neighborhood, which will be all the nodes that fit inside a certain radius row, as you can see stated also in colors, green and blue. Well, about the state of the art, some methods and some authors use the vector space model, which consists in putting all of the words of the array, all of the words of the document in an array, which does not capture the relationship among words. Also, other authors use the term weight in a matrix, which in this case, each entry represents a word of the document, and not all of the words appear in every document to be classified. And this becomes highly dimensional, resulting in a very large dispersed matrix. I'm sorry, I think my camera is not on. I'm sorry, I will continue my presentation now. Okay. As I was saying, some other authors also use the graph document representation to treat the documents as graph and use techniques to compare subgraphs and term graphs. In this case, for the term graphs, they treat each term of a graph as a web page using the PageRank score, which means that a page will have a higher score if it's being pointed by many other pages, or if it is pointed by a page that has already a high score. Also, the graphs and graphs kernels. Some authors also treat the document classification task as a graph classification task. And for this, they use the graph kernels, which can be defined as functions that measure the similarity of pairs of graphs. Okay, the proposal of this research, we have two contributions. The first one is the way to create feature vectors which are based on a document similarity comparison approach, as I mentioned and named before, using concepts of 3D models and graphs as the data structure to represent such documents. And the second contribution is the classification method itself, which is a new classification method which uses the representative feature vectors of each category mentioned in the first contribution. As long as the methodology goes, the steps are the pre-processing, the graph construction, the comparison, the feature vectors per category, the feature vector of a new document, and the classification method. Here we can observe a pipeline of the proposal and the whole methodology. As you can see on the left, we have first the categories of the documents. For each category, we do the pre-processing step, which consists on the removal of the stop words, which are words that does not bring any relevant information about the document, such as articles, prepositions, etc. After that, we perform the stemming step, in which we use the Porter algorithm, which maintains the roots of the words, because the words can have different gender, number, and to avoid all of that, we keep the roots. After that, we assign a numeric ID to these roots to a list, and then we proceed with the graph construction step. In this step, the nodes will be the IDs, the edges between nodes will be the relations shown in the document, and the weight of the edges will be the number of relations that appear in the document, and the weight of the node will be the summatory of all of its protruding edges weights. After that, we move to the comparison step. In the comparison step, we choose the keywords for each pair of documents to compare. The keywords will be defined as the nodes that has the higher values on its weight, and we took the intersection between each pair and use this with the intersection of the neighborhood, as I mentioned in the previous concept, and I will define it better later. After this, we get the comparison vectors B, which is the step C. And with this set of vectors B, we proceed to compute to get the feature vector per category, as you can see in step D. For this, we took each ID of the set of vectors B and get its frequency and order this in a decreasing way. And then by a certain parameter phi, we took this phi number of the frequency of elements for the feature vector D in step D. After this, we move to the bottom, and to perform the classification of a new unclassified document, we first take the document and apply the pre-processing steps, which will consist, again, elimination of stop words, stemming, and IDA assignment. So we get a vector, and with this one and the vectors for each category, we do the comparison method to obtain a belonging grade as a result, with which we will find to which category this new unclassified document belongs to. As I mentioned before, here's the comparison step, and the keywords for each graph are the nodes with greater weights, and the intersection of both lists contains the common keywords between both graphs, as shown in the next equation. Then, after we have the list of keywords, we find the neighborhood, and the neighborhood is denoted by the nodes which fit inside a certain radial row, and for this, in the graph creation step, we assign a weight to all the edges of the protruding nodes, right? So we apply the inverse of this so this way, the higher values of the weights will be the shortest now. And with this, we can apply the Dijkstra algorithm to get all of the nodes that fit inside a certain radial row. Then, instead of obtaining a comparison coefficient per each pair of documents, as was the goal of the previous approach that this research is being based on, we do the first contribution with this, which is perform a comparison between them to obtain the vectors B by the following equation, which will be the list of keywords plus the neighborhood of this. Then the feature vectors per category. To get this representative vectors gamma, we initially considered to apply the intersection of the vectors B, as stated in the pipeline, to obtain the common IDs of all vectors. But because of the low probability of a word being considered a keyword and also appearing in every document inside a category, this idea was dismissed. And also because in the experimentation step, the results of the intersection came to be 0, or the size of the resulting vector was too small. Well, instead of this, we obtain the occurrence frequencies delta of each word in the dictionary of all set of vectors B. And this frequencies vector is then ordered in a decreasing way to obtain the words with higher frequencies according to a threshold phi passed by parameter. And well, these resulting vectors gamma are obtained using the following equation, in which, as I mentioned before, will be the phi IDs with the highest frequencies inside of the set of the vectors B, obtained in the previous step of comparison. And in order to obtain a feature vector Z of a new unclassified document, first we do the preprocessing step, as I mentioned before. Then each ID will be placed as a position of the vector as it is shown in the next equation. And well, then moving on to the classification method. We found the intersection of this new vector of an unclassified document Z with all of the vectors gamma to each category. With this, we get the belonging grade X, for which we propose two methods. For the first one, the belonging grade X will be the number of elements of the intersection between Z and the vector gamma for each category. And the second method will be the belonging grade X will be the sum of the frequencies of the words in gamma that are in the intersection with Z. Well, after this, the category to which the new document will belong to will be the one with which it obtained the higher belonging grade X. Then we proceed to the experiment step. For this, we use the Amazon database, from which we randomly chose 4 categories and 8,000 documents, being 2,000 per category. The set of documents was then divided into 1,600 training documents and 400 testing documents. First, we get the vectors B from the training set. Then, by analyzing the obtained results, we can assign the value of the threshold phi, which controls how many IDs will be extracted for the classification method. The results of the category vectors B show values of delta superior to 3,000 and 10,000, and we use this. Well, this will become the assigned values to the threshold phi to get then the representative vectors per category gamma. By the time of getting the comparison vectors B per category, their sizes can be different as well as the size of the representative vector gamma. And because unlike the vector space model, in this method, it will not be necessary to complete elements inside these vectors to unify their sizes according to the dictionary of words. Here in the experimental results, we have which is the table of classification percentages with 4 categories. As we can see here, the categories are baby, DVD, software, toys, and games. And the results shown here are with the method 1 and the method 2, using a threshold phi of 3,000, 10,000, and different parameters as keywords 15, row 2, and grade K2. As you can see here, we have a high percentage of correctly classified documents in the diagonals of the table, and also this table shows the error percentage of misclassified documents in the other cells. Here we have the table of classification percentages with 3 categories, baby, DVD, and software, again with method 1, method 2, and different threshold and parameters, as long as with the error percentage of misclassified document. Here we have a better representation of the results. Here we have a bar chart of the percentages of the correctly classified documents in table 1, using method 1 and method 2, where each bar represents a different experiment. As you can see here, the parameters and the results. And here we have a bar chart of the percentages for the table 2 using method 1 and method 2. Here with this bar chart, we can observe that with method 1, the graphs does not vary that much as with the method 2. And well, some conclusions about the method. This method proved to have an average results from 75.5% up to 78.6% of correctly classified with 4 categories and 82.51% up to 89.3% with 3 categories. And we can observe that when performing experiments without the category toys and games, which generated a higher error percentage, the percentage of correct classified documents increases. Well, this is the reference of the previous paper of the same authors, a new graph-based approach for document similarity using concepts of non-rigid shapes. And well, I would like to acknowledge ILSA Investiga because the support of subvention for this research. Also to Cristian Lopez and Grimaldo Davila because they are the co-authors of this research. Thank you. That will be all from my side.
Thank you, Lorena. For the presentation, we will proceed with the questions. I invite Professor Ms. Ana Maria Cuadros to ask the first questions.
Okay, good job, Lorena. I have some questions about your investigation. First, how did you get the edge wedge of the graph?
Excuse me, can you repeat it, please?
How did you get the edge wedge of the graph?
Oh, okay. The edge weights for the graph will be the summatory. The edge weight of the graph will be the number of relations of these that appear in the document. So if that pair of nodes, that pair of IDs, that pair of words appear many times in the document, the number of times that they appear will be the number of the weight of that edge between those two nodes.
Okay. In the comparison section, what is the goal of equation number 6?
One second, please. Okay, are you referring to this
Oh,
equation?
excuse me, number 5. No,
This one?
no. In the document, the equation number 6 is other.
Yeah, I'm sorry, the equations are not numbered the same as in the paper. Can you tell me which part? I don't have the document in hand here right now. Can you please formulate the question again, please?
It's about find the neighborhood.
Oh, okay. I think you're referring this one, correct?
Okay, yes.
Okay, about the neighborhood. So the neighborhood is the adapt concept of the K-rings for documents. And here, after we get the weights of the edges between the nodes after the graph construction, we apply the inverse to these weights. So if the weight is bigger, the inverse will make it really smaller. And after this, we use the Dijkstra algorithm to get all of the nodes and all of the distances that will fit inside a certain radio row, which is also passed by parameter, which means that this neighborhood will be the words that are related to the keywords. And that will bring more information about the document because it will be the keywords and it will be the words related to those keywords.
Okay. And finally, what can you say about the scalability of the approach? For example, size of document, complexity, others.
Yes, that was considered to be in a future work, and this paper does not focus on that. And we were planning to continue the investigation and apply all of this in a future work.
Okay, it's all, Lorena. Thanks.
Thank you, Ana Maria. Now I invite Professor Christian Lopez to ask you questions.
Lorena, do you listen me? Right? Okay. First of all, really congratulations. Congratulations because it's not very common that the 3 or 4 cycle in the university, in undergraduate university, that some students can publish an article in an international event and more so in Europe. Now, I have 2 kind of questions, right? The first one is related to the article, and the second one is related about your experience in Italy. Okay, so you use the concept of K-ring, right?
Yeah.
So the idea is, what do you find the exact value of K? How do you find this value? How many rings do you need? 3 rings, 4 rings, 6 rings? How do you find the exact value of K?
Okay, well, we are choosing the value of K basing on the experimentation step. And because this is a new method, a new classification method, we don't have a predefined or a clearly defined way to get the best value for the parameters, which K will be a parameter. And we're basing just on the experimentation with which we get we got the best results. So that's how we are choosing K.
Okay, right. Now you have a document, you find the keywords, and you have different edges, different value of edges, but you now invert the value of the edges, invert the weights. Why you invert the weights?
Okay, yes, I invert the weights because the greater the weight, if I invert it, the smaller it will be. So with this value inverted, we can use, related to the previous question, we can use the Dijkstra algorithm to get the shortest path and the shortest distance to get the neighborhood. So this way, we will get all of the nodes that will be inside a certain radio, and that's how we get the neighborhood.
Right. But finally, I have a little question more, but it's about the keyword. How do you know when a word is a keyword? You use only the frequency of the word?
Okay, yes, a keyword, we can say that a word is a keyword after the graph creation step, where we assign the weights for the nodes, and the nodes will be the IDs. So after we assign the weights, we will get a list of all of the IDs and all of the weights, and we have a parameter there to get how many keywords we're going to have, and the keyword will be the ID or the node that has the higher weights. So we get the list in a decreasing way based on weights, and we get the highest weight. So that's how we know that it's a keyword.
Right. So now I have to do some question about your experience in Venecia, because it's very important for all other students to know what is the difference between some students from UNSA Peru, some students from the Italy, for example. Did you feel that the European students were as prepared as you, or better prepared than you? How do you feel about that?
Well, I think I don't have much expertise in that, and I can talk about many or any students from there. I just met the other presenters that were in the conference with me, and all that I can say is plenty of them were young. So I was expecting kind of seeing older people in there in the conference presenting, their articles, investigations. But I shook myself. I found myself finding pretty young people. Just I got the chance to speak a bit with a girl from China, and I was attending her presentation, and it was really, really good. And she was young. I didn't get the chance to ask her how old she was, but it was really, really good experience. And I can say that many young people are presenting to this kind of conference, so I think anyone can do it, no matter the age. So
It's real. But finally, what was the biggest problem that you faced in your investigation, in your research?
the biggest problem,
What was the bigger problem for you? Huh? What was the part the more difficult part in your research?
mm, the most
About
difficult
the
part about
research.
the research, I would say to translate it to English, because one way is to have the English you learn, as Latin American person, and other ways to have it like a native person. And for as much as you see the document and read it and search for mistakes, it's really hard to find if you are not native or you don't have a really good expertise in English.
Okay, thank you very much, Lorena. It's all on my side.
Thank you.
Thank you, Christian. First, I want to congratulate Lorena on her good job. I would like you to tell me about the implementation. What is the programming language did you use? What frameworks or libraries did you use? Finally, what is the computational cost from the query?
Okay. Yeah, this work was done in C++, using different libraries. For example, for the stemming part, we use the Porter algorithm. And About the complexity time, we didn't do much research, much analysis around that part. But yeah, I think it's kind of costly and can be better improved in a future approach.
That's okay, Lorena. It's important for students now and implementation. Once the questions are finished, we will proceed to deliberation. Lorena waits in the room while we deliberate.
Okay, thank you.
Ok, Lorena, ¿estás ahí?
Sí.
Ok, Anita, cámara, por favor. Bueno, finalizado el acto de sustentación, absueltas las preguntas, después de delibrar el jurado, vamos a dar lectura del acta de sustentación. Acta de sustentación número 29, título profesional de Ciencia de la Computación, bachiller Lorena Xiomara Castillo Galdos, en Arequipa, siendo las 15 horas del día 15 de diciembre del 2021, en la plataforma virtual del Duty por Google Meet, enlazándose mediante los correos electrónicos institucionales de la Universidad Nacional de San Agustín de Arequipa, en cumplimiento del decreto número 532/2021, TIPS, se reunió el jurado presidido por el profesor Juan Carlos Gutiérrez Cáceres, integrado por los profesores Dr. Cristian José López del Álamo, la doctora Ana María Cuadras Valdivia, dándose inicio al acto público de sustentación y evaluación de conformidad por el reglamento de grados y títulos vigente, correspondiente para optar el título profesional de licenciado en Ciencia de la Computación, en la que la bachiller Lorena Xiomara Castillo Galdos expuso la tesis titulada Document Classification Method Based on Graphs and Concepts of Non-Rigid 3D Models Approach. Tendida la sustentación, absuelta las observaciones y preguntas formuladas por cada uno de los miembros integrantes del jurado y efectuada la evaluación correspondiente, el resultado fue aprobado por unanimidad con felicitación pública, en fe de lo cual los miembros del jurado firman. Quiero felicitarte, Lorena. Quiero también exhortarte en esta nueva vida profesional, que siempre recuerdes a tu alma mater, que sigas guiando, llevando este emblema de la UNSA, Ciencia de la Computación, bien en alto, y que siempre te esperamos con los brazos abiertos para que nos puedas colaborar. Tenemos muchos estudiantes que están asistiendo. Como puedes ver, hay mucho trabajo por hacer, ¿no? Felicitaciones de nuevo. Eso sería todo. Gracias. Vamos a hacer un aplauso, ¿no?
Muchas gracias, profesor Juan Carlos, profesor Cristian, profesora Ana María. Gracias con todos.
Listo, muchas gracias. Felicitaciones, Lorena. Sigue adelante. Muy buen trabajo.
Felicitaciones, Lorena.
Ok.
Gracias.
Muchas gracias con todos. Si tengo clases, me retiro.
Listo, adiós. Cuídense, que les vaya bonito.
Chao, chao.